Okay, everybody. We're going to continue on our discussion of our kinetics and our chemical reactions unit. All right, and I just want to bring up the previous slide that we were talking about when it came to this collision theory. So we talked about mechanism, which is our pathway, right, of a reaction, the steps. And then we started talking about collision theory as becoming the theory on how something actually reacts. So if we take a look at the two things we mentioned about collision theory, we'll see that not only so basically particles have to collide in order to cause a chemical change, right? That's the most important thing. But there's two things that must be satisfied in order to form a successful collision. So the question is there a successful collision or an unsuccessful collision? A successful collision will give us a chemical change we're looking for. An unsuccessful collision will not, okay? And usually what the particles will do is they'll collide and pretty much bounce off one another without a collision and go back to what they were before. All right, so first you must collide with the proper orientation, which means those particles must collide in the right spot or the right angle. Okay, and next you're going to collide with just enough collision energy, the minimum amount of energy to cause that collision, and then you would get the intended effect. So the diagram just here was showing us that an ineffective collision where is if a CO molecule collided with an oxygen molecule, but the O's collide, which would create an ineffective collision and no products would form. But if that CO molecule turns around, okay, and the C contacts the O, okay, then you would form products. So it's not important what products you form here. It's more important that you actually get the reaction, okay? And then a fancy name for our collision energy is going to be called activation energy, which is simply the minimum amount of energy needed to react. What is that energy that's just enough so that you can cause a reaction? All right, and that's going to be again an energy in kilojoules. All right, so moving on, let's just say that we could take a look at some factors that would actually affect the collisions. I mean, we know we need collision energy. We know we need this certain orientation, but how can we increase those two or affect those two so that we could affect the rate, right? We could change it ourselves from the outside. All right, so I want you to think about people in a room, walking around a room, and see if we can figure out, and those people are the reactant particles. So see if we can figure this out. The first thing, okay, is just to think about what we need to do. So many times we're interested in speeding up or slowing down reactions. Okay, you can make you think about why we'd want to do this. Okay, and in anything that affects the collision effectiveness will increase or decrease the reaction rate. Again, those two things, we want to manipulate those two things. Okay, so number one is increasing the surface area. Okay, many times we know that if we chop up things or we increase the amount of particle surface that's involved in something, we usually get it to react faster. Again, think about wood. If you take wood and you chop up wood into sawdust or into small sticks, it usually burns faster than it would be if it was one large log. Okay, so more particles exposed to react. Okay, generally this happens when you're dealing with a lot of times with air. Okay, this also happens in the small intestine, right? So nutrients would be this large, the big surface area with all the sacs in the lungs and in the small intestine that causes the uptake of nutrients quicker. Okay, and usually when we have lumps or chunks of things like lumps of metal like this that would normally react at a certain rate, if we chop it up and we turn it into a powder, it generally would react much faster. Okay, so surface area is definitely something to investigate. Okay, so this would give us more chance of collision. Okay, when we talked about chance, we talk about the frequency of collisions, right? The frequency of collision, which is how often they collide. Okay. Now, again, if you want to talk about oftentimes collide, we can also talk about increasing the number of particles in a given space, right? Okay, so we can talk about the number of particles available in a space. Okay, and so if we put 100 molecules in a liter, maybe versus 10 molecules in a liter. Okay, and a good picture of this is maybe looking at concentration. Okay, so concentration is really important. You can see in here, if these were people walking around in a room, we can say, okay, if you had a lot of people 100 people walking around in a room here versus 10, that is more likely that these people would bump into each other than here, and there would be more chance of a collision. Again, you're increasing the frequency of collisions, just like you would be here. Again, you're increasing the frequency here of collisions. All right. Another one you can do. Okay. So maybe 100 molecules in a liter would be faster than 10 molecules in a liter. might be slower. Okay. Another interesting one, very similar to concentration, is just when we look at gases, and this will be only for gases. All right, so make sure you know your gases pretty well and what molecules and atoms are gases. Okay, and we can do this. So when we increase the pressure of gases, we're going to force more particles into less space, or we're going to take the same amount of particles and just limit the space that they can run around it. All right, so if you think about this picture, if I was to make the container smaller here, okay, in both, you would get that effect. All right, so again, sometimes this thing here is called a syringe. Okay, this thing is called, if I can change my pen here a little bit, if I go to black, we have, this is called a piston, okay, and this is called a cylinder. Okay, sometimes if this was a syringe, this would be a plunger, okay, or something like that. And if you slide this piston or this plunger in through the cylinder, you could change the space that those particles are in. So here's a certain amount of space here, and let's just say we double the space here. Okay, and we do that by changing something called the pressure. So this would be called a high pressure because we're pushing the cylinder in to limit the space. And this would be a low pressure going that way because we're giving it more space. Okay, now with the same amount of particles are here, and you can probably say here that you would increase the frequency of collisions here, right? Because particles are more likely to contact each other here and collide than they would be here. Okay, this would be a decrease in the frequency of collisions. All right. So nowhere in these three are we really talking about making the particles move faster. We're just increasing the frequency of the collisions, how often they collide. And again, the more often that they collide, the more chance there is for a successful collision. So we could think about low pressure is becoming a slower reaction than a high pressure, right? So we can make that assumption when we look at the number of particles. So if you think about what the particles are doing, okay, that would be a good way to think about common sense really with this. Okay, the next thing, okay, what we can do is we can add something called a catalyst. And what a catalyst is simply their helper molecules. Okay, when you add a catalyst, this is going to catalyst is going to help to lower the amount of energy required to react so that more particles will have the necessary energy for collisions. And that really helps. So less energy is needed for reaction, for collisions. Okay, this also provides an alternate reaction path, okay, which changes the mechanism on how the reaction takes place, makes that mechanism easier, okay? And good examples are enzymes in the body, catalytic converters in cars, okay, which also help change waste gas, okay, that are emitted by the vehicle. Okay, all cars have these catalytic converters. They call them catalysts because they're catalysts, right? So enzymes also work like this. So if you take a look at a catalyst, let's just say you had this purple and orange molecules to react, right? And you wanted to have them collide. Well, what a catalyst would do is a catalyst would go and bond to these guys and then help them collide or help them produce a new molecule. So here's your new molecule. And what did the catalyst really do? It's almost like a helper. It absorbed the purple and the green and the orange guy so that it would help them collide and get together and bond. And then what happens is it releases that product, and then this goes and repeats the process again. Okay, so that changes the mechanism. No longer are we relying on the chance of these collide. We're using a helper molecule. So this is a good little cartoon kind of thing. So catalysts, that's how catalysts and enzymes in the body work. They're almost like helper molecules. One other thing you want to realize on a catalyst also is that catalysts are regenerated and reusable. Okay? So you're always going to be able to, catalysts don't go away. They're not actually part of the reaction. Okay? They're a helper molecule that gets regenerated and used again. Okay, so it's important to know about a catalyst. Again, and the more we do, we're going to do more with catalysts later on, but this is the main idea. All right? But one last one, and this is number 5. Number 5 is really important. In fact, it's probably the most important one, and it's the easiest one because temperature is the special one. All right. And nowhere in the first four will we be talking about speed. Okay. A little bit here with a catalyst where you can use less energy. But when you increase the speed of the particles, okay, and again, remember what temperature is. This is your average kinetic energy, which equals the T in Kelvin. When you do that, you increase the amount of energy that these particles have. They actually go a lot faster. And when they collide, they move faster with more kinetic energy, which increases not only your collision frequency, but it also increases the amount of energy they have. So this really jacks up the collision rate, okay? And this is going to increase the rate more than any other factor that we've seen, okay? So it's really important to know. And if you take a look at the little picture here, we can see that particle A and particle B in the first picture with less temperature or less energy, these arrows are signifying that they're not moving that quickly. But when you really bring up the temperature, you can see they're moving a lot quicker in this little stationary photo. I wish I had a little better photo for you, but we'll be putting things up online. We'll see this in class also when I show you a couple of the reaction videos that we have. All right, so that's a really important. So not only does temperature increase the frequency, but it also gives you more energy of collision. All right, so again, these 5 things are really important. You want to make sure that you know that increasing all of these will increase the frequency or the speed or the number of collisions, which also increases the rate. But you can also reverse all 5 as well, and you can decrease the rate. So sometimes, again, we don't always want to speed up reactions. Sometimes we want to slow them down. So you can also manipulate. So you can use also these factors in combination. You don't have to use them separate. You can also, for example, you can add a catalyst and increase the temperature. Okay, or you could decrease the temperature and take a catalyst out to manipulate the reaction. Okay, so really important. Make sure you do your multiple choice questions on this. Make sure you go over this and understand it. Okay, and ask questions in class as well. All right. Last part of this is just really an infographic here. Again, if you look at this website, compoundchem.com, really great site for looking at these really, almost like posters of really interesting stuff that are very simple and very well thought out and very laid out nicely. And this is a good summary of what we just talked about. So if you get a chance to kind of read through this and take a look at it, you'll see this is all the factors that we saw. All right, and last but not least today is what I want to talk about is the form of a reaction. We'll go through this pretty quickly. Okay, really a reaction really looks like this. All right, if we just put out the important stuff here, okay, we can say A and B yields, that's how we read that arrow, or reacts to form. Okay, C and D, which is the products. Okay, and again, the reactants are going to take, this is what takes place before the reaction takes place. Okay, this is what we have beforehand, and this is a result of the reaction afterwards. Now, again, reactions are great. They're almost like recipes. What you don't see is what's happening in between. Okay, you don't see the moment of collision. You don't see how reactants are forming products. You don't see how they're forming. You just know what you have in the beginning, and you know what you have at the end. So think of it as a snapshot of both sides. Okay, all right. So that's the kind of good thing or the bad thing, I guess, about reactions. All right, so a good example is the creation of water. We're going to take 2 molecules of hydrogen and a molecule of oxygen, and then we're going to create 2 molecules of water. All right, so the physical state, some important things that you'll also see within a reaction is the physical state. We'll see a solid, we can see it as a liquid, we can see it as a gas, we can see it as AQ, and you can see this term will generally be a subscript after any subscripts that you see in the formula. You may or may not see them, sometimes they leave them out, sometimes they put them in, it depends on who's writing the reaction. Okay, just don't forget that a solution, remember this is a mixture here, and make sure you keep an eye on that mixture. There is water with this solution. All right, so heat can be if heat is written in the reaction, if it's on the right, it's going to be XO. And if heat is on the left, it's going to be an endothermic reaction. Remember, if heat is released here, right, and heat is absorbed here, okay, in this particular reaction, heat is going to be written on the right side because the creation of water is exothermic. And you remember this is also in kilojoules or joules. Forget. All right. A chemical equation must be balanced. Really important that it's balanced. Okay. We're going to get to that in the next video. Okay. And number 2. Okay. And I'm sorry, number 2. That's the end of that one. Okay. And again, we're balancing because we want conservation of mass. Again, the number of particles on the left side and the reactants must equal the number of particles of products of each type of element. So if you have 4 hydrogens here, you need to have 4 hydrogens here. If you have 2 oxygens here, then you're going to have 2 oxygens here. Remember, this 2 is going to go for both elements. Okay, and last but not least in this video is going to be the signs of a chemical change. We've done this before, a chemical reaction. If you give off heat or light, sometimes the word evolution means to give off. Okay, heat or light, or something evolves, that means given off. A formation of a gas, or sometimes you might even see bubbles for this. Okay, a formation of a precipitate or a solid. We're going to do a little bit more with this. This is the solid form during a reaction. Okay, and a color change or an odor change. Again, these 4 things would indicate that you probably have a chemical reaction. You rarely going to see all 4. You may just see one of them, or you may visually see none of them, and you need an instrument to figure out if you have a reaction or not. Sometimes reactions can be very slight or very extremely slow. Okay, so just a couple of things here that you might see. You can see this in here. You can see light in this video being released when you burn magnesium. Here, a temperature change, of course, when you're creating flames or a fire, a temperature change or some heat being generated. A production of a gas, you'll see bubbles here. Here's a good example of the precipitate. You'll see this yellow solid being formed within here. It looks like almost a cloudiness, which when you see cloudiness example is a precipitate. And again, a color change between these 2 test tubes would generally create this red solid. All right, so again, we're going to be seeing these things in class. Hang in there, do the best you can. Please bring questions to class, and make sure you take care of your questions to make sure that you understand. Okay, have a great day. Bye.